Regulations, there's all sorts of. Need to have a license currently. They're working on that too. Currently, you have to have both a CRT and a fluoro permit in the state of California. Physicians need to have a fluoro permit unless you're a board certified radiologist, in which case it's a slam dunk. The fluoro permit may go away and be incorporated into the CRT, which is what the RTCC recommended 25 years ago. The state said, no, we want a separate license for it. More money, different license fee. And in fact, at that time, the state was actually promoting, for people who wanted to do CT, that'd be a separate license, more money. If you want to do MR, separate license, more money. They were talking about if you wanted to do anything that was a special subset, special procedures. The committee, though, at least had good enough judgment to say, no, we're not going down that road. Okay. So you need a license. Operator exposure to scattered radiation is directly proportional to patient exposure. So whatever the patient gets is going to contribute to the scatter that's out in the room that can expose you. So if the patient suddenly has their exposure increased by a factor of 2, the amount of scatter out in the room is going to increase by a factor of 2. Likewise, if it goes down by a certain percentage, then what's out in the room is a certain percentage. So again, it's a small percentage, as we saw in the last presentation, but it's still connected. Lead apron has to be worn. 0.25 millimeter lead equivalent reduces scatter 97%. 0.5 is 99.9%. This is for 80 kVp. So when you read, the other thing is when you read these numbers, you have to know what kVp it was measured at. Okay, very important. You also must place them on hangers. Now the original lead aprons that had thin lead between 2 sheets of rubber would crack if you just dropped them on the ground, and as they aged, they would crack. Some of you may be in facilities that are still using old aprons. You shouldn't be. They should all be gone by this time. The new lead equivalent materials are actually an alloy, so there's no lead in them. But still, you want to place them on hangers so everything stays smooth. You don't want to run the risk of developing cracks. Mostly it's tears. So if you drop them on the ground and somebody kicks them or equipment rolls across them and they get torn, then that means the lead equivalent material inside alloy could also be torn. MA and KV have to be visibly indicated. So any room that you work in, if you can't look at the control console and tell what KV and MA the equipment is operating at during fluoro or radiography, or fluoro especially, if you can't tell, something's wrong. It's illegal. You need to monitor that once a week. And it can be any kind of, can be any phantom that mimics 7 7/8 inches of lucite. At Kaiser, you may see techs, if you're working nights, usually the night tech gets stuck doing this. You'll see that it's a 9-inch steel plate that they use to just measure output under certain prescribed machine settings. But you have to look at that once a week, every week. The state will come in and during their survey, they will look at your records to see if you're doing it once a week. And you have to keep records for at least 3 years. Okay, that's called your fluoro stability test. There's also a movement to have that replaced and done away with. I agree with that one. It really doesn't tell you anything. What the regulation says is if the output, if you measure the KV and MA every week, if it changes sufficiently that the exposure to the patient changes by 25%, then you have to record that the system is being sent for, or going to be serviced. So to do that, you need to know, okay, well, if the MA changes account for a certain percentage change in dose, KV is not linear, it's a power function, so you have to look what that plot is, and but if they both change, you need to know what the combined effect is. We actually used a computer program to draw a chart. State loved it, but it's like, that's awfully complicated, and we never found that test to be indicative of any equipment problem in the 25 years that I was testing equipment. It's crazy. So anyway, but still, it's required until they change it. You must wear your dosimeter. Where do we wear our dosimeters?
On the collar.
Okay, you can't just point to the neck.
Collar.
Collar.
You wear it at the collar level, outside any protective lead. Okay? And inspectors look for that. You don't want to be caught without it. Worst thing I've seen is inspectors going in and asking, "Excuse me, where's your dosimeter?" Tech reaches into his pocket and goes, "Oh, it's right here." What's your name? Ladies, if you are pregnant, where do you wear your dosimeter?
2 dosimeters, one here, one underneath the apron, on the
One
level
at
of the
the
belly.
abdomen, underneath the apron. So you're wearing how many total?
2.
2. Good. Okay, good.
Yeah,
Excellent.
thank you.
If you have a piece of equipment like we have in the back, fortunately a lot of those systems don't exist anymore, but if they do, you want to make sure the Bucky slot cover is covered and that there's a curtain to keep scatter away from you. There's some ISO exposure profiles. So this is for an under table x-ray tube, II on top. This is just for proportional because it doesn't tell you what the technique is. So unfortunately you can't say that at X kV MA this is what you get. But anyway, so this is with no curtain, no Bucky slot covered. You get some scatter set out in the room, but if you put a protective curtain, like you'll see in the back room, and you keep this slot closed, then that reduces the amount of scatter considerably. Basically, all you get is the scatter out towards the head and out towards the feet. Mobile screens generally are 1 to 2 millimeter lead equivalent. For some of the mobile equipment that I'm going to show you when we do the lecture on mobiles, I tell facilities they should go get one of the nuclear medicine shields that have considerably more lead in them because it's almost like doing a CT. And there's one person that always has to stay in the room, and that's the anesthesiologist. Curtain is 0.25. Bucky slot cover is 0.25. Gloves. This is wrong. This is a borrowed exam, sorry. The lead gloves for fluoro rooms, these are all 0.5. That's why when you're working and you don't have a gonadal shield for a child or an adult male, those lead gloves work really well. They're soft, they are conformable, so you can shape them around the anatomy that you need to, and they do meet the 0.5 millimeter lead equivalency. Thyroid shields are 0.25. So this is a typical example. Bucky slot covers closed because the Bucky's all at the extreme end. These are your curtains, lead curtains. The only thing I would say is that this is way too far above the patient. That should be a lot closer. So that's just a closer. Lead glasses, goggles, face shields. I have a problem with goggles and glasses. It's really kind of interesting. There was research done back in the 70s and published that, of course, people forgot because most people now doing this are a lot younger than I am and they've never read this stuff. But they actually did some experimentation with a phantom head like this, wearing lead glasses, both this type and the type with the side shield, and looking at whether those had any effect on eye exposure. And the effect was surprising, that in many cases, eye exposure was increased. And the reason for that was because this is leaded glass. As long as you're looking at the direct source of scatter, you're fine. Anybody worked in special procedures yet? No? Okay, a few of you? So, if Kat is the patient and I'm the radiologist, okay, where am I looking? Where did you see the radio? Was I looking at the patient? No. Where am I looking?
The screen.
I'm looking at a bank of monitors up here or up there. So I'm doing something like this, or I'm doing this, or doing something else. I'm not looking where my eyes are being protected. So what they found in this experiment was that if you are receiving scattered exposure to something where it's not direct to the glasses, it goes through your head, through your eyes, hits the lead glass, and what happens? You get backscatter. So they actually found, because of the geometry and how the glasses were worn, there were significant opportunities for eye exposure to go up due to backscatter. So I like devices like this. They're much nicer. They're very light. They go from ear all around to ear for those physicians or technologists that wear glasses. Plenty of room for that. It's adjustable up and down. Also acts as a splash guard. So you don't need to have an extra splash guard in special procedure. You just need to have your mask. And it's great. This costs really no more than this. Yes?
So, Mr. McDermott, do you suggest we wear leaded glasses?
Should I get some custom-made ones?
Like for you, would you wear for you? Let's say if you don't want to give advice like that, like would you be wearing them or not yourself?
I have never worn lead glasses in my life for any procedure. Because I always worked in rooms that had hanging shields, which is what you should have in a room. So if you have hanging shields and it's over the patient, now you have this huge cone of protection. You don't need glasses for protection. You've got that hanging shield. If your room doesn't have hanging shields and you're doing special procedures or high fluoro procedures, I have no objections, and I think it's probably worth it if you're doing table-side work to have something to take care of your eyes. But if Kat's the patient and you're just monitoring equipment from here, maybe you can have a rolling shield. But the only people I ever had an eye exposure problem with were the radiologists who were doing table-side work and refused to use their hanging shield. It's the only time I had issues.
So, like with a C-arm, kind of close. What do you think about that?
Oh, C-arm in surgery?
Mm-hmm.
So, C-arms aren't putting out that much. I think it really depends on where you are. Most technologists, you're not that close, and we can talk about this more when we do mobile lecture, but you're not that close. You know, the people that in a surgical situation, that there's 3 individuals that are always close to the patient: the surgeon, the scrub nurse, anesthesiologist. Now, there may be a second assistant surgeon, so you'd have 4, but everybody else, for the most part, they're moving. They're walking around. They're doing stuff. They're carrying stuff. They're packing stuff up. They're doing stuff. that there's only those groups that are close by. The best protection that you can have when you're working in a room with a physician, whether it's surgery or fluoro, whatever, stand behind the doctor. That gives you a body, lead, and distance. Perfectly safe. I would tell nurses that when there weren't enough lead aprons available and they were going to make an exposure, I always told them, find a doctor, get behind them. They were dosimetered, so I could see what kind of exposure they got. They never got anything to mention. I mean, you just have to be wise and realize what the scatter looks like and who's really involved and how it affects you. Now, in some rooms too, there are new devices where, in addition to your dosimeter, which is a true measurement device and it's legal, they have little sensors that you wear, and as you move around, there's a display that says, are you red, yellow, or green? Red, yellow, and green are specific exposure levels in the room. So as you're walking around, if you look up at this thing and you're red, it's like, oh, okay, now I'm good, I'm green. That helps you determine what types of, because every patient, every procedure is different. You can do the procedure in the morning and standing here this far away from Kat, you're perfectly safe in the green. Next patient can come in and you're the patient and I'm standing in the same place and oh my God, I'm in the red. It depends. And those are great devices. Most of the special procedures rooms have them, so look for those. And but those don't read levels. That just tells you what zone you're in. But they're good. They're a good tool. So this is correct. If you're pregnant, this is correct. That's okay.
That's okay.
Yeah, see, these are the types of things I always got into because every dosimeter manufacturer, and if you're using Landauer's especially, I know, every dosimeter is marked with a body part indicator. So it actually says, is it an extremity? Is it arm, shoulder, collar, chest, abdomen, different types of places. So you have to, if you're wearing a dosimeter that's marked for chest, then you can't wear it up here. It's going to give a wrong reading. You need to have whoever manages your dosimeters make that change so that they're actually doing a collar dosimeter. So at Kaiser, I made sure they were all collar dosimeters, ring dosimeters for our nuclear medicine and ultrasound personnel, and fetal baby monitors for women that declared their pregnancy. Dosimeters, minimum exposure of 10, this is old. This was for the old film type. The Landauer newer ones are good down to 1 milliround. And to way above 700. There are filters. The error on a Landauer badge, for example, is only plus or minus 10%. The film is 25%. The nice part about film is it is a permanent record. TLDs.
Luminescent.
Thank you. Thermoluminescent dosimeters are not, because you read them out by heating them up. They give off light. You measure the light, and it tells you how much exposure you got. The problem is you cannot reread the badge. For film, yes, you can. Film ages, so you do get some decrease in accuracy. The Landauer type of technology they use, which has crystals in it, basically you only read part of it, and it goes into storage. It does not degrade. And you can go back and reread that dosimeter 5, 10, 15, 20 years in the future. Film is heat sensitive, the others are not. Oh, so now we're talking TLDs. So TLDs, 9% error, goes down to 5. Reusable, not heat sensitive per se. They have to be heated at a very high temperature. Lithium fluoride, they are no permanent record. OSL, this is what I like. Minimum exposure, 1 millirem. Actually, the accuracy is 1% or better. Reusable, they're rugged, they're aluminum oxide. You can leave these in your car, nothing's going to happen. Not like film. Film suffers from heat, heat turns it dark. The darkness on the film can be read as radiation exposure. I actually had that issue to a nurse who was working in a neonatal intensive care. She worked 3 nights a week, during which they may do 1 x-ray. This is the night shift, so they may do 1 x-ray, and she came out with 35,000 millirem on her dosimeter. That was a problem, as you can imagine. Turns out she went on vacation. She was gone for a month during the month of August. Car was parked outside. She left her dosimeter in the car, and the heat turned it black, but apparently there was enough protection that it didn't make the emulsion crisp, kind of like burnt pizza. So when it was read out, it came back with very high exposure. So please realize, the readings on your dosimeter is presumptive evidence legally of exposure. It's the one case where you are guilty until they can prove you innocent. So to prove this nurse innocent, after we looked at her work history and going, where did she get this? Sent her to UCLA. She had to have some bone marrow drawn so they could look at, remember we talked about looking at chromosome damage, and you could determine 25R or above. They couldn't, so we knew it was below that. And then we found out what she did, and it was like, sent it back to the lab and said, could this possibly be heat? And they came back and said yes. So had to send that to the state. State had to say yes, thank you very much. We can now change that exposure to something legal. I had to make a guess at what her usual was. That whole process took 6 months, and she had some restricted duties at work, which was not fair, but that's the way it is. So you want to wear it, and you want to know that it's a legal device and is presumptive evidence of exposure. And this is how the optically stimulated luminescent type works. They excite it with a laser. It stimulates emission, and it's read by a photodiode. But they only do a small area, so anything that hasn't been zapped by the laser can be reread over and over and over again. It's pretty cool. If you were to look at this physically, it looks like a small piece of sandpaper. It's exactly what it is. Pretty cool. Pocket dosimeters are still used. Was the original dosimeter that was used during the early atomic age. There is no permanent record. It's calibrated. It's sensitive to shock. The reading is very subjective, has a limited dose range, and it can be used in addition to OSL. OSL, or any dosimeter, you wear for, how long do you wear yours? A month?
3 months.
3 months. Oh, you're on quarterly. Oh.
Well,
Okay.
a student.
I just prefer monthly myself. So you're wearing that, so that's a period of time. But if you're doing something that might be particularly hazardous, a special procedure where you think your dose might be higher, then we can do as a one-time use, you can wear something like this. So you charge it. What's inside of this is, I don't know, does she have a picture? No, she doesn't. So what's inside of this is radiation ionizes this. So what you do is you set up a current between the anode and the cathode. There's a little hair wire in here and a scale, and as radiation hits it, it creates ions, and that little hair moves. And because it's in a calibrated device, you can actually read it. So usually these things can read from 0 to 200 MR. Some of them can read 0 to 500 MR. So these were used for very short, single experiment type things. Maybe a single procedure. Maybe if you're doing a new procedure and you want to know what technologists get doing this new procedure, you might wear one of these and have it read at the end of it. But then you have to make a record. And those records have to be kept, just like your dosimeter records have to be kept for lifetime. You have audible warning devices. These are usually used by first responders. There's detectors in here. They're preset for certain levels, so if they're responding to an accident where radiation or radioactive materials might be, if this goes off, it tells them, oops, you're someplace where you're getting at least a certain level of exposure. Usually there's also a reading up on top so you can see at some point when you have to leave. Absorbed dose is energy absorbed in tissue. Equivalent dose is absorbed dose times the RBE, factor relative biologic effectiveness. For X-rays, that's 1. Neutrons are 10, alphas are 20. Effective dose is a method of converting non-uniform radiation dose to a dose as if the whole body were exposed. So there's a whole table of effective doses. So if I expose Kat's arm, there's a way of, that's going to show up as an effective dose, saying that arm exposure is equivalent to how much exposure to her entire body. And that's what effective dose does. Exposure is measured by ionization. Exposure is the only thing measured. And you measure the ionization, and it's measured in Röntgen. After that, everything else is a calculation. Okay. Dose equivalent, whole body, you are limited to 0.05 sieverts a year. Skin or extremities are 0.5. Lens of the eye, 0.15 sieverts. And the public is 0.002 millirem per hour, or 0.1 rem per year. Yes?
Can you go back to the last slide?
The last slide? I have to go backwards? Okay.
That one, yeah.
That one?
We don't have the definitions.
I'm sorry?
Oh, the definitions are not on the PowerPoint.
Really?
Slide.
Oh,
Can we get the new one?
your PowerPoint should look just like this. Bad, Lynn. Bad, Ms. Smith. I have to talk to her about that. Well, thank you for stopping me. Let me know when I can go. Select red, green. Okay. All good? Ready? Oh, yeah, see, there she goes. Okay. All right. So this is what the public does. When we do shielding designs for room, any public area has to be calculated to meet this. So if there's a waiting room next to your x-ray room, it has to meet these requirements. Notifications. There are high radiation areas, which means you can get 0.1 rem or 100 millirem in an hour. A radiation area is 5 millirem in an hour. Okay. And those would be posted. Okay. I love some of these new nomenclatures. When I was working, I'm sorry, we had no idea what a TPD is. Sounds like a disease.
No, that's STD.
Hmm?
That's a little different. That's a little different abbreviation.
Anyway, so patient ESE is higher and magnification is greater when the fluoroscopic X-ray tube is too close to the tabletop. So if it's down here versus it up here. Okay. Total filtration minimum is 2.5 millimeters aluminum. Usually it's around 3, but 2.5 is the minimum. Beam intensity should not exceed 2.2 R per minute per MA. That's rule of thumb. Typically that's, you can measure that, and it comes out to be pretty right on. Tabletop. By regulation, the aluminum equivalency of the tabletop should be less than 1 millimeter at 100 kVp. That's because you don't want the tabletop to be absorbing a lot of X-rays. You want it to be pretty radiolucent. That keeps everybody's exposure down. Gonadal shielding, we already talked. 0.5 millimeters lead, and there's contact, so you can have flat, or I don't know why they keep this in the desk, or you can have shaped gonadal shielding for the guys.
Is that a baseball cut?
Huh? What?
I was like, is that a baseball cut?
Well, no, the shielding's not, but putting it on can be.
Do they come in different sizes?
I'm sorry? What?
Do they come in different sizes?
Yes, they do, actually. Thank you very much for reminding me. Yes, they do come in different sizes. Small, medium, and Russian.
Oh, extra large, okay.
See? There we go. So you got contact shield, you got the one I just showed you. There are also shields that you can put, they're called shadow shields. You attach them to the tube. They don't show them here, but you put it on the tube, and you, wherever the shadow is, that means that area is shielded. Scatter radiation, 90 degrees to the patient. Kind of tells you what's going on here. Okay. Patient holding. Dun, dun, dun. Okay. When we talked about having somebody other than you hold a patient, that's essentially true. However, you may hold, as a technologist, in violation of state law, in an emergency. So, if you're in a situation where there is nobody available, and you need to hold, that's fine. But you want to report it to your supervisor and make it clear to them what the nature of the emergency was and that it was justified that you hold. They would probably do an incident report so that it's on file, so should any inspector, any agency, surveying group, because the surveys look through all that stuff. Should they ask questions, then you can justify, yes, the technologist in question did hold the patient in this particular situation due to an emergency situation. So it's not routine. Students, no. Some places will try to say, oh, we can use students for this. That would be a no. And if you're being asked to do that, you need to let Ms. Mitz or Dr. P know. Okay, that's not a good idea. And of course, for holding patients, you always want to make sure the person holding is provided with appropriate shielding. Under versus over is just the two different types of situation. X-ray tube above is mostly, the scatter is going to be mostly in your eyes. That's why you want a hanging shield here. Kind of takes care of that. If it's under X-ray, it's going to be mostly towards what? Feet. And there have been cases recorded of X-ray dermatitis to radiologists' feet. Not so much in the fixed rooms, but in most of your, bless you,
Bless you.
in most of your special procedures rooms, using a C-arm type device, they almost always have the image intensifier on top, the X-ray tube down here. Radiologist's apron ends slightly below the knees. Now, I never had or saw a case, in my experience, of radiation dermatitis of a radiologist's feet. And if I was going to see it, I would have seen it with 3 physicians that I could think of. But it is possible, so you do want to at least be aware of that. This is again above and below. This tells you just the difference between all of this. Again, the tabletop has to be very radiolucent. Patient is supine in both of these. So, dose to pelvic organs 8 centimeters deep to the skin in A and B. So in this particular situation, it's 2. In this situation, it's 8. Or 2 and 27, which makes sense. If you're looking at something that's only 8 centimeters deep anteriorly, you're going to have all of this attenuation here versus very little attenuation here. So that makes perfect sense. That's one of the things to be aware of. Overhead tube, image intensifier with digital converter. We've talked about all that type of equipment stuff. In this case, the X-ray tube is under the table. This is X-ray tube above, and this is a typical remote room, which means you can either operate it from table side or remotely. So you reduce dose by time, which is directly proportional to exposure. Shielding, increase shielding, decrease exposure. And distance, inversely proportional to the distance squared. So if you move from 1 feet to 2 feet, you've doubled the distance, you've decreased your exposure by a factor of 4. If you go from 1 foot to 3 feet, you've reduced it by 3 squared, which is by a factor of 9. Okay? And you do the reverse if you move closer. So distance is your friend, probably as much or if not more than shielding. If you can move back away from the source of scatter, your protection increases very rapidly as you take just one giant step back. And if you take a giant step back and move behind the physician, you're good. People always laugh at that, but physicians make great shields. They really do.
Well, plus they're wearing
They
the
can't
apron
move.
too.
They can't move. Well, even if they don't wear their
Mhm,
apron, you
but
still
then
have
they're
the
wearing-
body. You know, some of our radiologists are heavy. Okay, distance. If at 1 foot the intensity is 500 MR per hour and you remain there for 6 minutes, you receive what? 50 R, right? What happens to your exposure if you move 2 feet away and remain there for 3 minutes?
12.5.
Oh, she doesn't give the answers. Oh, wait, that's going to be in your exercise. There we go. The 1 foot, then there's all sorts of examples. You just have to use inverse square to determine